So Chris Karnauskas calls this the atmospheric interface. So obviously it's the air-sea interface, and then he gets into describing how the atmosphere responds to the ocean. So it's a kind of a quick run through the atmospheric circulation, but not meant to be a pedagogical lecture on atmospheric dynamics, but just what is required to explain the ocean's role in climate. So the first contrast is to start by looking at the ocean temperature structure and the atmospheric temperature structure. Here are in meters, so this is about 5 kilometers down to the bottom on average, and in general, if you take average profile, this is in the western tropical Pacific, so the sea surface temperatures are fairly warm. So you can see that the temperatures very quickly drop in the thermocline and match the deeper ocean temperatures by a kilometer or so, but the atmosphere on the other hand cools much less rapidly, and here is the tropopause at more than 15 kilometers, because in the western Pacific there is a lot of deep convection, tall clouds, so the troposphere is tropopause is higher, and then you have ozone formation and the stratosphere, of course. And if you zoom into the 750 meters in both the ocean and the atmosphere, you can see the contrast much more clearly. So you have the profiles from various sources, balloons, and the array, the mooring in the ocean. Here the mooring only goes down to 750 meters or so, and then the dotted line here is a extrapolation. But you can see the stark contrast between how sharp the gradient of temperature is in the ocean near the surface in the top 200 meters versus the top 750 meters in the atmosphere, where the temperature barely changes, especially in the western Pacific, where there is deep convection that is mixing temperatures in the atmosphere. Especially if you look at the equivalent potential temperature, you will basically see nearly vertical line because of the convection. So how do the responses happen? This is the idealized vertical structure of the atmosphere in terms of temperature in 3 simple steps. So if you think about the sun's energy coming in, taking out the albedo related shortwave loss, we have seen when we did radiative equilibrium calculations that the surface receives short wave and emits long wave. So you have warm near long wave emission source, which keeps the temperature warm near the surface, and as you go up in the atmosphere, temperature begins to drop off, as we have already seen several times. And the main important effect of a greenhouse atmosphere is that the surface temperature is much warmer than it would otherwise be if there was no atmosphere and the surface was directly emitting long wave to space, as we saw before. Now keep that profile here and see how it changes at the upper atmosphere and the tropopause into the stratosphere, because you have this is warm because it's close to the sun technically, but also because it is absorbing UV, splitting oxygen into oxygen molecules into oxygen atoms, forming ozone. Ozone is absorbing UV, so we get a warming stratosphere. And when you look at the profile up to the thermosphere, we see that the troposphere has a lapse rate which is negative, so dt dz is less than 0, as we already know. And of course it depends on whether you're talking about dry adiabat like over the desert or moist adiabat like the western Pacific that we talked about in the previous slide, and so on. And the stratosphere has always got dt dz greater than 0, and it can of course change based on season and so on. Above that you have again stratopause and mesosphere, mesophause and thermosphere. The energy balances change, density of the air begins to drop, molecules to lose the outgoing long wave energy to space, begin to drop, and then ozone here again creates a warming, and the thermosphere in fact can get very warm. That's why it's called the thermosphere. Above that you get the ionosphere, where the gas molecules are basically ions, and you cannot use the black body radiation kind of calculations anymore, and so on. So that's a quick recap of the energy balance that gave us the vertical profile that we had seen before already. If we now look at the top of the atmosphere fluxes, the solar radiation at the top of the atmosphere you expect is going to be high, order 400 watts per meter squared. In the low latitudes, we are in a sphere, and the sun's rays coming in are almost parallel, but because of the curvature, we have much less energy per unit area at higher latitudes, so the energy received from the sun drops off. Of course, there is a seasonality, because north of the polar circles we know that there is 6 months of darkness and 6 months of daylight, diffuse daylight. So doing all that, annual mean looks like this. The outgoing long wave radiation, which we will look at in a bit more detail in the next slide, looks a bit complicated, but depends on, again, just sigma t to the fourth. This is what is coming at the top of the atmosphere. So remember that this is reflected solar plus long wave. So this is total outgoing radiation and not just outgoing long wave radiation. So it's a bit complicated, because higher albedo regions also have positive values here, because they are reflecting sunlight as well. Okay, so this is a little bit complicated because it's mixing the ITCZ, the subtropical gyres, the deserts, and so on with the albedo and the outgoing long wave radiation. The net here, the net radiation incoming minus outgoing gives us what we expect, with high values here in the Indo-Pacific warm pool region, and drops off with latitude as we expect. So combination of cold sea surface temperatures, clouds, albedo, and so on give you a pattern that looks almost like sea surface temperature here. So you have cold temperatures here, warm temperatures here, cold temperatures here, and so on, and then the subtropical gyres, subpolar gyres, and high latitudes. So this is a different way of depicting it, but you get the picture. This is what we saw before. The net radiation, when you do the zonal mean over all longitudes, has a deficit beyond certain latitude in both hemispheres, and a surplus in the latitude band here, and you can see that's because the incoming energy is higher here than the outgoing energy. This is albedo times solar constant plus outgoing long wave. So this is the energy surplus region, this is the energy deficit region. Obviously, to prevent the tropics from getting warmer and warmer from this energy, and the poles getting colder and colder from this deficit, we have to move energy from here to there, which is what gives us the whole Hadley cell, Ferrel cell, polar cell, ocean circulation, ocean and atmosphere, heat transport, and so on and so forth. So looking at the outgoing long wave now, more specifically than just the outgoing radiation, you see this is OLR averaged over 1 day, 1 week, 1 month, 1 year, and 1 decade, and there are subtle differences. If you look at any particular day, the planet is covered by a lot of clouds, because this is October 29, 2012. So depending on the season, each hemisphere will have its summer, winter, fall, spring, and that determines how much cloud cover there is. Of course, in the deep tropics you always have rainfall, and the ITCZ structures still seen here. African monsoon, Amazonian rain, and so on are seen here as well. And there are reasons why there are these tilting structures, which are related to the eddy transports and so on. And you have outgoing long wave radiation from different types of clouds as well. Okay, nonetheless, clouds have generally lower OLR. These white colors here correspond to lower OLR because cloud top temperatures are colder, so you have sigma T to the fourth that is lower, whereas when the OLR is coming from the surface, warmer temperatures, especially over deserts, are emitting high OLR, and subtropical gyres as well. But as you begin to average over time, you can see that the cloud cover gets smoothed out, and these regions get smoothed out and get different shapes. You can see here gets narrower here, a little bit more narrow here. ITCZ becomes much better defined as you average longer and longer, and you can see the OLR values here are much lower than here, for example. Deserts remain almost the same, but other regions you can see much smaller depending on and lower depending on the averaging period. But there are of course permanent cloudy, low cloud regions. This is a stratus deck cold temperature region where you have high OLR all the time. So you can see high OLR persists all the time, even though there is a change in averaging. Southern Ocean is different, as you can see. It remains similar, even though it's brighter here, and then remains almost the same for 1 month, 1 year, and 1 decade. So these kinds of details matter for the energy balance, atmospheric circulation, and various time scales that are occurring in the weather and in climate. For example, weather you think is related to sun going up, sun going down, so there is a daily forcing of solar radiation, and sun goes north and south, so there is a seasonal forcing of radiation. So there is a strong seasonal cycle in most places, some places more than the others, but within a day weather can change multiple times because of these feedbacks. Depending on where you are, you can have sea breeze, land breeze, moving convections, rainfall, sunny mornings, afternoon rain, and so on and so forth. So within a day, weather can change because there are lots of internal feedbacks, and these are often related to land atmosphere and ocean atmosphere feedbacks. We will focus on the ocean, so we'll look at ocean atmosphere feedbacks later on in this chapter when we come to looking at how the atmosphere responds to ocean forcing, which will become clearer. Some of it we have already looked at before in terms of El Niños and monsoons and so on and so forth. We will revisit these in a slightly different take from Chris Karnauskas in building to ocean's role in climate. Okay.